Right, welcome. So in this session, we are going to um we are going to continue what we started with hyperparameter tuning, and this is going to be the last iteration. And we've looked at grid search, which is a form of hyperparameter tuning, where we consider every single combination of hyperparameters within the parameter grid, every single combination. And we saw that the weakness of that is can be very slow, can be very computationally expensive, especially when your grid is large. Although it guarantees that you find the best parameters within your own specified grid. However, then we looked at randomized search, which is simpler, not more efficient, but it is simpler than grid search. And the simplicity comes from the fact that we are not evaluating all of the combination of hyperparameters within the grid. We are only just considering a sample of that particular population. And the choice of that sample is going to be the number of elements that we are sampling out is going to be determined by this value of number of iteration. And we saw that the weakness of that is, well, there is no decision really, there is no information that goes into how we sample, right? We just, before we even begin, before randomized search begins to train at all, it's just going to like do the sampling out. Whether that combination of hyperparameter helps, whether it does not help, it does not care. It just samples out and find the best within that particular range. However, sometimes you want to do something that is way more efficient, that is something that uh, is much more powerful than randomized search and not as expensive computationally as grid search. And that is where a library like Optuna comes in. So, and it uses the concept of Bayesian optimization. Let's see, with Optuna. Let's say Optuna, right? Optuna like this. So it uses this idea of conditional probability where um, we do not just sample out all of those combination of hyperparameters that we want to use. We start by using some random. We start by training some model on a random hyperparameter, right? And we begin to tweak those hyperparameters, and try to see whether that actually leads us to um, maximizing the objective function. And in the case of minimization, we'll see whether the tweak also help us to minimize, whether the tweak that we make to hyperparameter prior to the next step that we are taking, does it actually guide us? Does it take us closer to our objective function, our goal? So how does Optuna work? The first thing we want to do is we want to import Optuna. Let's see, we are still up. It says no module found. Perfect. So what you want to do, you have something like this is you want to start by installing Optuna. So you say pip install Optuna. So it's important that you run that first. So once that is done, I'm just going to delete that, but don't forget it's extremely important. I'm going to give this another spin. So Optuna is working now. And in Optuna, there are just a few steps. So the first step, Optuna also uses Plotly, so you might just want to import Plotly. I don't know if we have Plotly yet. So it's import Plotly express as px. Great. So let's see if our parameter grid is still actually we are going to define it manually. I'm going to define it. Okay, great. So I'm going to define it differently though. So what are the steps that we are going to use in, so don't forget we are still using the O flow from this particular script. So should we do that or just define a new one? Let's do that. So it's the same. No, let's write it from scratch so that this video can actually be like a standalone video that you can watch even if you didn't watch the previous two. So we're going to get a new data set out. What data set did we use? The last one is the tips data set. That's going to require cleaning so much. If not too much, but I don't want us to spend majority of time on that. So I'm just going to do from sklearn. Let's do that. Let's get, so I'm just going to have to copy like a handful of code. So I'm going to get this and paste that here. I'm going to get column transformer and root mean squared error. Let me just copy these three because I need cross validation score also. So I'm going to come here and paste that. I do not need key fold really, and I'm not going to train a base model. You should, however, train a base model, but I'm not doing that. So I'm going to run this. Then the other thing I'm going to do is come to this place. I might need train test split. I'm going to paste this here. Then I need train test split. So I'm going to come to model selection and say train. You already know how all of these things work. So then I can run this. And the next thing to do after that is to pre-process the data. All of this pre-processing, we'll do it again just for people that are watching, probably watching only this video. And what's the pre-processing that we are doing? We are actually combining the process of encoding and scaling. We are combining it into one pre-processing pipeline, and we are using column transformer. So what we did on this line is grab all of the names of the numeric columns that we want to scale and the names of the categorical columns that we want to encode. Then we get an instance of encoder, an instance of one not encoder actually, and another instance of scalar. Then we pass it in the pipeline like so. After that, we feed and transform everything in the pipeline. We run that. What other thing do we have to do? We don't need to train a base model. We already have it here. So we can actually proceed to the Optuna part now. So how do we actually um, set up Optuna training? So how do we actually do that? The way to do that is to, step one is to define the objective function. The objective function. So I can say def objective, and inside it we're going to have trial, and this bit is important. And it returns a float, so you can go ahead and say float if you want. If you understand type annotation. Then objective trial, and the next thing for us to do is to actually set up each of those hyperparameters. So in our parameter grid, we only have criterion and max depth. So I can say max underscore depth. And this is where I like to set up mine. That's going to be trial. Max depth is integer. So that's going to be trial dot suggest underscore int. And what do I want to suggest? I want to suggest max depth, and I want to do so from 2 to 21 like we have in our parameter grid. Then criterion, I want to do trial dot suggest underscore categorical, and that's going to be criterion, the name of the stuff, and I'm going to pass in a list. So since that is I can't remember all of them, so I'm just going to copy all of this, then paste it in here. Great. So now we've set up the two of the stuff that we need. So the next thing I'm going to do is create a regressor model. I'm going to say regressor equals, since you are using decision trees regressor, I'm going to say max depth is going to be the max depth that we've created, and criterion is going to be equals to the criterion that we've created, and random state is going to be equals to 23 for reproducibility. Great. Then the next thing for us to do is to, excuse me, next thing for us to do is to actually set up um s- our food. We're going to say score equals cross val score, and this is particularly important because Optuna allows you to do anything that you want, but it does not really help you undo cross validation by itself, the way grid search and randomized search do. So I'm going to say estimator equals regressor. X is going to be equals to x underscore trained underscore transformed. Y is going to be equals to y underscore train. Scoring is going to be equals to negative root mean squared error. Neg root mean squared error. Then CV is going to be equals to k underscore food dot split x underscore train underscore transformed. And what else? I think that is all. Scoring, XY scoring. Yeah, that's everything is fine. And since this we expect a single value, cross validation. If you follow cross val score, if you follow the previous classes, returns an array of score, like corresponding with the number of food that we have here. So, but our score should be one thing. So I'm just going to average it out. So I'm going to say dot mean here, and also we need to add negative here. You can do it anytime. Don't forget that this negative root mean square error returns negative because we are trying to trick this thing. So what we are going to do is I'm going to multiply negative minus so that it cancels out. So once that is done, I think the next thing to do is to return score, right? So I mean it is very flexible, so you can really do anything that you want. So the next thing to do is to create study. Step 2 is we are going to create a study. I'm going to say study equals Optuna dot create study, and inside study we are going to pass in a few parameters, and you know the parameters that we're going to create, they are listed here, although I could show you that um in the in their documentation also, but we're going to pass in objective. We're going to say objective, and we are going to actually get sampler. Actually, we should let's come here. I'm going to show you this. So we are going to say sampler equals Optuna dot sampler. So sampler is how you do random state in Optuna, right? But there is no random state. We call it Optuna samplers, random samplers. So we can say seed equals 23. So really, let me show you this. Let me show you the doc so you don't feel like, I mean, you can always come to their doc. All of these things I know because I've uh had to use Optuna a few times, but you don't have to. It's not like anything is set in stone really. So this is their doc. If you come to code example, you're going to see implementation for anything. You can use it to literally optimize a mathematical function, scikit-learn, sgboost, anything, pytorch. So I come to scikit-learn here. So this is what we've done this. We've created our trial. You're going to see that they didn't like really, really. I mean, they followed our implementation in a way, but they are using two different um, classifiers in their case here. So yeah, this is where we are on currently. So direction, when we do create study, we have to pass direction equals something, then sampler, then we optimize it. So we come here. This is not objective. That's a mistake. This is supposed to be direction. So their direction in this case is maximized because this is if you look at the metrics, is accuracy. But in our case, our metrics is RMSE, so it is going to be minimize, and they didn't include sampler in theirs here, but you know we could do that. Then the next thing is to actually optimize the study. So we say study dot optimize and passing objective, like so, exactly what they did. Yeah. Then the next thing is the number of trials I want to do. Like randomized search, it does not evaluate everything, it only evaluate for a specific number of trials. So let's do the same thing that we did for randomized search, which is 50. So we run that and we see what's happening. All right. So I think that should, yeah. So that has started running, and yeah. So what you are going to see here is, although we are training for the same 50 iterations that we did in you know um randomized search, but in the case of Optuna, it did not just like sample all of those combination of 50 combinations of hyperparameter beforehand. It started with trial zero, like, okay, trial zero is just going to be some values of hyperparameters. Max depth equals 12, criterion equals squared error. Then it tries to just choose another. Then if that one like is better than the previous one, we keep exploring that area. But if not, we revert back. So that is what is happening here. You see, best try is zero. When we tested trial one, it was not better than zero. We stuck with zero. Then two, you see, like that. We keep going like that till it was stuck on trial seven for a while. Like trial seven was the best trial for, I feel like, the longest, maybe all the way. Imagine all the way. So trial seven remained the best trial, like till the end of the whole thing. And we can come here and actually do um study dot best params normal. So you see, max depth equals 3, criterion equals squared error, which um is the same thing that we have for grid search, right? So uh it shows you, it confirms to you just how powerful Optuna can be. So it is much more like much more efficient than randomized search, and it tries to really get close to the performance of grid search without really like using that much compute. And another thing that you can do is you can actually visualize uh plots. Is that right? I think you could do that by saying Optuna dot visualization dot plot, for example, importances of study. So this one is going to return the importance of each of the hyperparameters. And what we found in the last class that criterion is not that important is going to be obvious now. So can you see? So it shows us that 87% of the variation that we see from changing each of the hyperparameters comes from max depth. Like majority of the variation actually comes from max depth, and only 13% comes from criterion. So criterion is more or less not uh, that important like that, like that. Then another thing that you could check is you could do Optuna dot plot dot visualization dot plot. You can plot param called optimization history. Yeah, I think that's the one. Shows us how the whole thing went. And you're going to see a scatter plot. Exactly. You're going to see a scatter plot with this. So we see how the model moved and just could not really beat this, right? Just found convergence here and it just maintain that. So these are all of the other points, and they do not take us closer to the goal, right? So and we found that around 7 here, I think, here. So from here we found some score at 12 that was at trial 12 that was um the same score as this, another one at 23 the same score, but we didn't find anything that beats this. And if you are working on maximization, let's say accuracy, it's going to be something that goes up like this instead of coming down like this. Then you can plot parallel coordinates also to see each of the. You can actually check their dog. You're going to see a lot of um, different visuals that helps you like gain insight into what happened during training. So if we do parallel coordinates, which is the last one we're going to be looking at. Okay, cool. So what you see is if you check max depth, you're going to see that majority of what contributes to um what do you call it here? The goal is to make the objective function smaller to minimize, which is 1.12. You're going to see that it comes from uh, max depth, right? So comes from max depth here, and you're going to see that it actually this line thickens as we go down, like for max depth, Friedman MSC, even max depth and squared error. You're going to see it here, and you're going to see that for some more of the other values here, especially for uh, anything that's large max depth, from 8 up to 21, they all come here, just like this broom thing, they all come here and they like bounce off, like just diverges, right? Went up for higher values of RMSC, and you see that the guys that come from here, this max depth, this smaller max depth, around 2 to 4, goes into squared error. And yeah, the another interesting one is max depth between, I think, 2 to around 6, goes into Freeman MSC and also comes down in a way, right? So it means that max depth of around 3 thereabout with Friedman MSC also leads to some smaller value in objective function. So yeah, that is your that is optional for you. That is Bayesian optimization. with hyperparameter tuning. So hyperparameter tuning is an extremely important part of training a supervised learning model, and that's how you do it. So usually, I tend to use Bayesian optimization more in my personal projects at work, because it gives you that sweet balance between what grid search offers and what randomized search offers. So thank you, and see you in the next one.